Hello mathematicians, let's have a look at our next topic, the geometry of the derivative. Now we know what the derivative is. The derivative is just the differential of a function, or a relation for that matter. So we know that that can be denoted if y equals f of x, for example, then we could be talking about y dashed, we could be talking about f dashed of x, we could be talking about dy dx, and the process of getting these is called differentiation. So with that in mind, let's take a look at this topic. So we're going to start off looking at increasing, decreasing, and stationary at a point with regard to a curve or a function. So the first differential of a curve we know is a measure of the slope or the gradient of the curve. So that when we find the slope, what we're really doing is finding the rate of change of y with respect to x. In other words, dy dx, which is the slope of the curve at any point. Now, if f of x is some function, and it's actually defined at a particular spot, x equals a, then we can say that if f dashed of a, so if the slope of the curve at the point a is greater than 0, so it's got a positive slope, so it's tending up to the right, then f of x is an increasing function at x equals a. So for the curve on our right here, this blue part is all the parts of the curve where the function is increasing, or all the values of a, if you like, for which f dashed of a is positive, greater than 0. If f dashed of a is less than 0, then we've got a decreasing function. So the slope is always negative. So if the slope is always positive, the curve has to always be increasing in size. And if the slope is always negative, the value of the function always has to be getting smaller. So it's a decreasing function. And right at the very top of this curve, we've got that if the first differential at that spot is 0, which means that the tangent to the curve is horizontal, then f of x is called a stationary or f dashed of x, sorry, f of x is called a stationary function at that point where x equals a. So we've got increasing function anywhere where the slope of the tangent is positive, a stationary function where it's 0, and a decreasing function anywhere where the slope is negative. So let's have a look at these examples. The first one is to determine where this particular function is stationary. So we know that a curve is stationary at f dashed of x equals 0. So that's our condition for a stationary point. So our first task is to find f dashed of x. Now we could multiply this out, or we could apply the product rule. So since it's written as a product, put down the first, multiply it by the differential of the second, plus put down the second, and multiply it by the differential of the first, which is 1. So that will give us x plus x is 2x, and minus 2 minus 4 is minus 6. So f dashed of x equals 2x minus 6. We require f dashed of x equals 0 for a stationary point, so therefore we want 2x minus 6 to equal 0 for a stationary point. That is, x will equal 3. So when x equals 3, we have a stationary point. So we should give the coordinates of the point. So that is when x equals 3. And if we put that value of 3 back up into this curve, that will give us 3 minus 2, which is 1, and 3 minus 4, which is minus 1. Which gives us a product of minus 1, is the stationary point. Next one, show that y equals 1 on x has no stationary point. So that means that we need to show that there is nowhere that f dashed of x equals 0. So again, our first step is to find f dashed of x. Now when we see y equals 1 on x, we know what to do with these, and that is to realise that really that's saying y, or f of x, I guess I should have just stuck to y, f of x equals x to the minus 1, that's 1 on x. So when I differentiate that, that will give me minus 1 x to the minus 2, which is 1 on x squared. Now, 1 on x squared is not equal to 0 for any x. So we can't make 1 on x squared equal to 0 because we would need the numerator to be 0 and the numerator is 1. We can't change that. So regardless of the value of x, knowing that we're not allowed to have x equal 0, so regardless of the value of x, we can't make f dash of x equals 0. So therefore f dash of x is not equal to 0, so no stationary point. No stationary point. For our next example, we want where this function is decreasing. So what's the condition for decreasing? It's decreasing if y dashed or f dashed is less than 0. So this then means that we want, first of all, to find y dashed. So that's going to be 3x squared minus 4. Therefore, we require 3x squared minus 4 to be less than 0. So that's 3x squared less than 4. So x squared less than 4 on 3. So when we think about this x squared less than 4 on 3, we have to be a little bit careful. So think back to this parabola just here. We know that that's a parabola which is concave up and it's going to cut at minus 4. And where it cuts will be at plus square root of 4 on 3 and minus square root of 4 on 3. Now where is that parabola less than 0? It's in this part just here. So we're looking for the values of x between minus the square root of 4 on 3, which is minus 2 on root 3, and plus 2 on root 3. And again, we just have to be careful to remember that this parabola is the parabola representing the slope of this function. This here is not a drawing of this function because this is a cubic. So let's have a look at our next example. So the first part says find f dash of x. So we can see that we've got a quotient here. So f dash of x is going to be found by the quotient rule, which means that we take the bottom, put it down the bottom and square it. Then we put it up the top. Then we multiply by the differential of the top, which will be 2x, minus, put down the top, and multiply by the differential of the bottom, which will be 2x. So when we come to that, we now multiply things out and gather them together. So we're going to have a 2x cubed here, and from this part here we'll have a minus 2x cubed. So that goes. We've got a minus 2x and a plus 8x, so that's going to be plus 6x over x squared minus 1 all squared. So that's our f dash of x. Now this next part is just reading. So it says establish that f dash of x, so that's our differential, is less than 0 when x is less than 0. And this has got a mistake in it. That should say when x is not equal to minus 1. And you can see that the reason for that is that if x did equal minus 1, when we squared that, our bottom line would become 1 minus 1, which is 0. We're not allowed to divide by 0. But for any other value of x less than 0, this bottom will be positive because it's something squared, and the top will be negative because x is less than 0. So that means that f dash of x will be less than 0. Now, likewise, to get f dash of x to be greater than 0, again, the bottom is always positive except when x equals 1, because that would make the bottom 0, so the whole thing would be undefined. But it's always positive, so if we have our values of x which are positive, then our whole fraction will be positive. So now we know that the slope is always negative for less than 0, always positive for greater than 0, but we can't have x equaling plus or minus 1 and have the slope defined. So what does our curve look like? Well, first of all, if we go back to our original function here, we can see that we're not allowed to have x equal plus or minus 1. So if this is our set of axes here, x's and y's, we're not allowed to have the curve exist at plus 1 and minus 1. So that's the reason that the differential can't exist at those points, because the curve doesn't exist. It's not continuous. And we do know that for less than 0, f dash of x has to be negative, which means we've got a negative slope, and for greater than 0 it's going to be positive. Now let's think about what happens when x equals 0. When x equals 0, we've got minus 4 divided by minus 1, which is plus 4. So we know that we cut through the y-axis just there at 4. We're going to cut the x-axis where y equals 0, so that will be when the top is 0. And given that this is x minus 2, x plus 2, that will happen at plus 2 and at minus 2. We're going to pass through the x-axis. Now, when x equals 0, we said that we have the y value as 4, but when x equals 0, we also have f dash of x equals 0, which means that the slope of the tangent just there, or the slope of the curve, is equal to 0. So the curve has a slope of 0 there, which means that it's either going to dip down to a minimum or go up to a maximum, as we've encountered with the parabola. So if we put all of these clues together, knowing that we need negative slope less than 0 and positive slope greater than 0, then this is what we get as our best guess for the shape of the curve, our sketch of the curve. We could go through and work out limits for what happens as x tends to infinity, plus infinity and minus infinity. And we could work out limits as we tend towards 1 from the positive side and from the negative side. But at this stage, we're just trying to get a sense of the shape of the curve. Now, if we have a look at this example, we need to be careful to make sure that we actually get our head around the problem and remember what things we actually know. So it says, look carefully at this function below, establish where it's increasing. So we know that that's simply wherever the slope of the function is positive. It's decreasing, so that's wherever the slope is negative. And it's stationary wherever the slope is 0. So if we glance at this, we can see that at this point, this point, this point, and this point, the slope is 0. And leading up to that point just there, the slope is positive. It's negative all the way here, positive all the way here, negative, positive. So if we're going to draw on the same set of axes as this, the slope, so we're going to draw y dashed against x, so this is the graph of the derivative or the slope, then this graph is going to be 0 there and there and here and here. And if we look at these tangents here, very roughly drawn, we can see that we've got positive values which are getting smaller and smaller and smaller as we head to 0, and then negative values getting bigger and bigger and bigger as we head towards a maximum value right where it crosses. So what our curve is going to look like is these positive values getting smaller and smaller until just they're 0, and then negative values getting bigger and bigger until they reach their biggest value just opposite this spot here. Then they're still negative, but they're getting less and less negative until we're at 0 again at this spot. Then they're going to go up. They're always positive. This is the biggest positive. Then the positive value gets smaller and smaller back to 0. Then we're going negative, positive, and away we go like that. So this is our graph of y dashed versus x. So these problems require real attention to detail, but there are only these points that we have to work with. So have a go at the evens now in 10A, please.